Okay, I had somebody ask a question about some graphs of logs and what log properties are involved, and also taking the derivative of those. So I thought I'd use Desmos to show the different sequences of transformations. So what we are asked is about this function, y equals log base 10 of 2x plus 100 to the third power. And we're asked about the base parent function being log base 10 of x. So I know a couple things, and one of those that I'm going to address first is that this third power right here up on the log function is hard to understand as a transformation. It's hard to visualize what happens to a graph when you cube all of the y values. And so that's challenging to think about. But if we remember that raising the input to a power using a log property means you're actually just multiplying the front of the logarithm. And I actually should clarify, I misspoke a second ago because the 3, the cube, was not cubing the original y values. It was actually cubing the 2x plus 100. So it's kind of cubing the x values instead of cubing the y values. So I misspoke. But anyway, log property says you can take the power on the input and multiply it in front of the logarithm, and then it's a lot easier to recognize what's happening. You're multiplying the old y values by 3. So the 3 right there is a vertical dilation, or you can say stretch by 3. So our new graph is going to be 3 times taller than our old graph. When you do things on the inside of the parentheses, it kind of works backwards of how you might expect it. So while multiplying 3 in front of the logarithm made it 3 times taller, you might think that multiplying by 2 on the inside makes it 2 times wider, but it's actually backwards. It makes it half as wide. One way to think about that is that multiplying makes things makes your outputs larger. And there's sort of two things that happen when you make your outputs larger. Your graph gets taller, but your graph also appears to get skinnier. You can see this very readily if you look at like an example of like if I multiply 2x squared like that, that becomes 2 squared, 4x squared. So the idea there is that twice as skinny makes it 4 times as tall. The same general idea is true for every function, that if you multiply on the inside, it gets skinnier, which usually also makes it taller. So the horizontal dilation I'm going to write 1/2 to show you that it's getting half as wide. And then the tricky thing about the 100 is recognizing if it is shifting it to the left or shifting it to the right. And this one is shifting left by 50. You might say, wait, where did the 50 come from? Well, if you factor 2x plus 100, you can see that it's 2 times x plus 50. And when we factor things, we often think about what number would make the inside parentheses equal 0. And that's why we get a shifting left by 50, because it would take a negative 50 to counteract the x plus 50 in the parentheses. So if it's been a while since you've done function transformations, that probably felt like a lot of information. But if you're familiar with it, that should feel like things you've done before. And there we go. All right, so let's see what happened. Did we get it right? All right, so it definitely got shifted left by 50 because the asymptote used to be at x equals 0. Now it's at x equals negative 50. It does look like it's taller. It's hard to recognize the narrowness, but that is what happened, is that it made it half as wide with respect to the vertical asymptote. So it's a little hard to see right here, but the blue curve is closer to its vertical asymptote than the red curve is. It's half as wide, and it's also 3 times as tall. So it makes it a little bit more of a sharp angled turn as you go. Okay, then this next thing that the question asked us to do was to calculate the derivative, dy dx. And so there's two ways you can do it. One way is using the original function and just saying that's the log of an inside function. And when you take the derivative of a logarithm, it's useful to first write it in terms of natural log because natural log has a 1 over x derivative. So I'm going to write this as natural log of the input divided by natural log of the base. You can also just remember that you're dividing by the natural log of base, which is kind of like when you take the derivative of an exponential function, you multiply by the natural log of the base. So either way, either rewrite it or memorize that. Okay, so when I do dy dx, I've got the 1 over natural log of 10. Then I've got derivative of the natural log, which says 1 divided by the inside function, multiplied by the derivative of the inside function. And you can see that a lot of things cancel out because this is 2x plus 100 squared. Oh, oops, I'm missing one thing. Derivative of the inside function has another chain rule, so another times 2. Okay, so this is the inside function squared, so the third power cancels. So I end up with just 6, 3 times 2, over natural log of 10 times 2x plus 100. That's dy dx. Another way I could have done it was by using the transformed version of the equation, like I talked about when I was talking about the graph transformations. And then you can see the 3 is just a constant. You have 1 over natural log of 10 times 1 over 2x plus 100 times the derivative of the inside. And that matches exactly up with the other answer. So there you go. Let me know if you got any questions. Happy to help out.